Hello everyone. Oops, I'll start again. Hello everyone. Good morning or good afternoon, depending on where we are. Um, so um, Today I want to tell you about the Cuntz semigroup and the way to use this Cuntz semigroup to understand the structure and the classification of sister algebras. So the plan, oops. The plan is to start with an introduction and at the same time some motivation behind the study of the Kuhn semigroup. Then I'll formally define and tell you about the structure of the Kuhn semigroup. And then I'll end with various results. Some of them I was part of in terms of obtaining them. And hopefully, after all of this, you'll find that indeed the Kuhn semigroup is a very interesting tool, and hopefully you'll find applications yourself. Okay, so I'm assuming that you have seen the construction of K0 group. If not, then when I'm going to formally define the Kuhn semigroup, you'll notice that this is just a version of the K0 group of a unital sister algebra. The main idea is that you replace projections with positive elements. So you relax the condition as opposed to just projections, you allow positive elements. And the equivalence relation is also slightly modified, as I'm going to explain later. Now, it's important to say that initially, the semigroup that we are about to discuss was introduced by Cuntz, Joachim Cuntz, and his interest was into traces showing the existence of quasi-traces on stably finite sister algebras. It is only actually recently, relatively recently now, that people in the field of classification, well, interested in the classification sister algebra became very interested. And that's thanks to Andrew Tom's breakthrough, where he actually constructed two simple sister algebra. I'm giving more details on the slide. So simple separable unital nuclear satisfies the UCT, such that the Elliott invariant, which I'm going to talk about more later, but let's just assume that you have heard something about it. So it's essentially K-theory and traces. So the Elliott invariant of the two sister algebra A and B is the same, so you cannot distinguish. However, the algebras are not isomorphic, and the way to see that is using the Kuhn semigroup. So this paper, this result, this breakthrough was the starting point of where people said, well, if we want to classify, we should pay attention on the Kuhn semigroup. So now, when you introduce a new object into the classification theory or in any field, you look for advantages and disadvantages. Now, the main advantage is that if you have a non-zero sister algebra, then obviously you have plenty of positive elements, right? So the moment you have a non-zero element X, then X star is a positive element. So the Kuhn semigroup will be non-trivial. On the other hand, we know for K-theory, so I'm trying to use this analogy with K-theory, we know that there are stable projectionless, now it's algebras with no projections, in which case the K-theory is trivial. It tells you nothing about the algebra. So obviously at this moment, you may say, well, this makes sense. So why not just forget about the K-theory and work with Kuhn semigroup? Obviously, there are downsides. So it would be nice if this will actually be the case, but there are disadvantages. And the main disadvantage at the moment is that the calculation of the Kuhn semigroup seem to be harder. Actually, arguably, you can say that it will be out of reach in some cases. And I'm going to discuss that shortly. Unless, as opposed to K-theory, well, we know we have nice techniques, like, for instance, the six-term exact sequence or the Pimsner-Vercolescu sequence for certain cross products. So there are nice ways to calculate the K-groups. For Kuhn semigroup, it is not only that we are at the beginning, but it turns out that indeed the calculations seem to be out of reach, at least in many cases. So I want you to kind of keep in mind that indeed Kuhn semigroup copies in many ways the K-theory. However, K0 groups, I should say, of unital sister algebras, but all of a sudden we notice that it becomes very, very complicated. Okay, so here's a formal definition of the Cuntz semigroup, and I'm actually going to use the original definition that Joachim Cuntz more than 4 years ago used. So first of all, M infinity here. So what I mean by M infinity, I'm not sure if I can, this is the arbitrary union of matrices over the algebra A. And by this plus, I mean, I'm looking at positive elements. And on purpose, I'm not talking about the stabilization, now it's the closure of this. And we say that A is a Cuntz less than B if I can find the sequence of elements Vn in M infinity of A, such that the cut down, so if you cut down B by Vn and Vn star, left and right, this converges in norm to A. So this is what we mean by A is Cuntz subequivalent with B. And then we can define A is a Cuntz equivalent with B if A is Cuntz subequivalent with B and B is Cuntz subequivalent with A. And it takes some work, but you can show that this is indeed an equivalence relation. So like I said, back in 1978, Joachim Cuntz introduced what we now call the classical Cuntz semigroup. So notice when I'm using the W, I'm referring to the original Cuntz semigroup definition. And what is important to pay attention is that he is looking at this algebra, which is not closed, M infinity of A. So you look at the positive elements here and you quotient by the equivalence relation I just mentioned. And recently, in 2008, about the same time that Andrew Thoms announced his important result, in a joint work with Chris Coward and George Elliott, we made a minor change, what looks like a minor change. But I'm going to try to argue that this is actually a very useful modification. So we introduced what we call the stabilized version of the Cuntz semigroup. So what we did, we basically changed. So in the definition, we changed the M infinity by the closure. In other words, A tensor K, K is the algebra of compact operators. So everything stays the same, except we introduce the closure. And indeed, in the first instance, this looks like a very minor change. Almost you wonder, what's the point? I mean, of course, Joachim knew about it. I mean, it's impossible that he wasn't aware of this. I'm going to explain now why this is meaningful and why likely was not considered earlier. So first of all, let's look at some calculations, and I'm going to explain the significance of our closure using these calculations. So the first calculation is Cuntz of C. So you start with the algebra C. Now, because of the stabilization, this will be the same thing as Cuntz of Mn of C, of course. And the result is that this is going to be the natural numbers union with infinity. So this is important, the fact that infinity has to be there. If you think about the classical Cuntz semigroup, you will not get the infinity there. Now, there is another calculation, which I'm actually going to explain a little bit how is obtained. So if you look at the Cuntz semigroup of continuous function over 0, 1. Now, obviously, because of the stabilization, this will be the same thing as a continuous function of 0, 1 with values in matrices, or if you like, values compact operators. And it turns out this is going to be the set of functions which are lower semi-continuous with values inside of semigroup, well, inside of natural numbers union with infinity. And yes,
for non-expert. So what corresponds to this infinity point, for instance, which
infinite rank. If you have a compact operator of infinite rank. Okay. And now what I want you to actually pay attention is that, say I replace the closed interval 0, 1 with the cube. To date, now, as far as I know, nobody has a calculation and an answer for this Cuntz semigroup. If you compare this with the K theory, because this cube is contractible, the K0 is actually going to be Z just because it's contractible. So what we notice here is that the Cuntz semigroup is actually picking up a lot of details. So the K-theory of the continuous function of the cube is the same thing as the K-theory of the continuous function, let's say, on the interval. Both of them are Z. So the K-theory, K0, I should say, does not pick up the dimension. However, the Cuntz semigroup, already in this case, we don't know what it is. That's probably one disadvantage. But, yeah, question.
Yes, can I ask? You say that F is lower semi-continuous. It means that you are looking at Cuntz semigroup as a topological group, or at least in this case, N union infinity is compactification.
Okay, so what I'm saying here is I'm not looking at that as a topological group. I'm actually saying that I'm looking at the semigroup of lower. So these functions, I can add them point-wise.
Ah.
So this is going to be a semigroup. Okay. So I'm not concerned about the topology. What I'm concerned about is the semigroup structure.
Okay. So maybe a naive question, but was this the semigroup of C01 square?
Yeah, exactly.
It was confused.
Yes, I'm actually going to answer this question in my next couple of slides. So yes, so I think we know what happens in the 0, 1 square. In fact, the result, I will mention it, I believe, if not the next slide, a slide after. So I'll answer that. So first, let me say a few words about how we obtain, because I think there are important facts that are being used. So if I want to describe a little bit how we calculate the Cuntz semigroup of the complex numbers, or Mn of C, what we use is actually a fact which likely you have seen it before, I hope. So two operators acting on the same Hilbert space in general cannot be diagonalized at the same time unless they commute. Now, what's very interesting is that if I take the Cuntz classes, so now I take all the positive operators, I do the quotient. What I claim is that two Cuntz classes can be diagonalized at the same time. And let me explain what I mean by that. So say Cuntz of A and Cuntz, I have two classes, class of A and class of B. Now for any A in the first class, I claim that I can find B in the second class such that both of them are diagonalized at the same time. Now, why is this significant? Well, then I can compare the two Cuntz classes. If I can diagonalize at the same time, I can say that if one has rank, say, 2 and the other one has rank 4, then the one which has rank 4 is going to dominate Cuntz, in sense of Cuntz, is going to dominate the first class. So the significance of this is that it allows us to use the rank function to find the isomorphism. So when we look at this, this result, this calculation, I'm using the rank function. And the detail that one uses is that indeed the Cuntz classes, you can diagonalize at the same time. Now, regarding the calculation of the Cuntz of C01, what happens is in the first observation is that this is a point-wise calculation. So if you evaluate your function, let's say anywhere between 0 and 1, that's like having complex numbers. So in a certain sense, what you do here, you try to glue together all these calculations. Now, this obviously sounds easy, but there is still one more important detail. And that is this statement here, which says that if you have a continuous function with value matrices or compact operators, you can approximate this by diagonal matrix valued functions. So now, because these are diagonal, you can also ask whether the eigenvalues are in a decreasing order. And this is a result due to George Eliot. Very important technical detail. So using this, you can actually conclude that indeed you can identify this with a lower semi-continuous function. So the idea is that a lower semi-continuous function is obtained as an increasing sequence of continuous functions, and then those you can actually manage because you can arrange them to have this diagonal form. And now to answer the question, what happens with the 0, 1 square of the square? First, let me introduce a notation. So we denote LSC of sigma. These are going to be lower semi-continuous function from X with values in natural numbers union with infinity, such that the pre-image of the n infinity. So first of all, because it's lower semi-continuous, this pre-image is going to be an open set but we require that this is a sigma compact, meaning that it's a countable union of compact sets for all n. Then Lionel Robert showed the following theorem, which I think to date, at least in my knowledge, this is the best calculation of the Cuntz semigroup we have so far. Says the following, that if X is a locally compact Hausdorff space with covering dimension at most 2, and Czech cohomology is the second group of Czech cohomology is trivial. Now, why is this condition? Because the Euler class of a fiber bundle will be 0. So that means you don't allow any non-trivial bundles. Then he shows that the Cuntz semigroup is actually precisely this semigroup of lower semi-continuous function, which has this property that the pre-image is sigma compact. So this will include the square. This calculation will include the square because obviously the covering dimension is at most 2 in this theorem.
Non-trivial bundles, U1 bundles, I mean, circle bundles? Or...
I'm sorry, can you repeat the question?
Vector bundles, what do you mean? Like second check class, it's about U1, no? About circle, associated bundles with circle bundles. You say any non-trivial bundle.
Yes, so this condition is to guarantee that we don't have any non-trivial bundles over X. Because this will tell me that the Euler class is gonna vanish.
Okay.
Yes.
Yeah, it's okay.
Okay.
Yeah. Okay, so I probably should mention that the dimension X equals 0. This was originally due to it appears in Francis Pereira paper. And also the dimension, the X equals the interval 0, 1 was an implicit way in my thesis, which was done under the supervision of George Eliot. Okay, so as a summary, here are some calculations, the ones I mentioned, and something additional, which likely I will mention later on in my talk. So we have complex numbers, matrices, algebra of compact operators, and also I want to make a comparison to the K0. So for the complex numbers and Mn of C, we know we have Z for the K theory. We have the Cuntz semigroup is N union with infinity. For two unfactors, one can check that the Cuntz semigroup is this disjoint union, and I will say more about this. Now I will explain what's the significance of this disjoint union later on in my talk. And now for continuous over 0, 1, we just talked about, and then the Z here is actually of Jiangsu algebra. And it turns out that this V sub A, this is the Murai-von Neumann semigroup, which is the natural numbers, and the K theory is going to be Z. And the Cuntz semigroup turns out to be N disjoint union with 0 infinity. Okay, so at this stage, probably one question likely you may have is, why not define from the beginning the classical Cuntz semigroup as being this closure that recently we introduced? And there is a good reason for why not define it like this. So the first observation is that you do get infinity into your calculation. So you get the equivalence class of infinity. Now, as we probably know from the construction of the K0, you have to take the enveloping Grothendieck group to get a group out of the semigroup. But now if you have infinity, then this enveloping group is going to be trivial. So if you still want to get a group, you essentially have to avoid having the infinity in the semigroup.
Can you hear me?
Yes.
Am I right to remember, I mean, is it correct what I remember that this effect of trivializing the Grothendieck group when you have infinity is called Eilenberg swindle? That's the trick?
Yes, I think you're right. Yes. Thank you. Yeah.
Francesco?
So what we decided is to use the semigroup. So usually what happens is group obviously are much easier to deal with. However, the decision is that we want to use the semigroup. And actually, this is an interesting observation. Going from the semigroup to the group, information is being lost. Now, the trade is that the calculations of these semigroups tend to be very, very complicated, and the object is much harder to work with. As I mentioned at the beginning, the advantages versus disadvantages. So working with the semigroup turns out to be much more difficult.
Does it happen to usual K theory also? K0. Also there, no? You lose some information.
Say it again?
For usual K0, you also lose some information by going to a group, no? Group and group trick from semigroup.
Yes. Yes. So what I'm pointing out is that the decision was that we want to stick with the semigroup and pay the price because the usual calculations with the semigroups are much harder.
Okay.
Now, like I said, if we take the closure, then your group is going to be trivial, so you lost everything. You have no information captured by the group. Now, when we did this closure, we also noticed, and this is actually for people working in the classification program, was a very important result. So this is in my joint work with Chris Coward and George Elliott. So what we show is that this stabilized version of the Cuntz semigroup is continuous relative to inductive limits, meaning that if I have an inductive limit and I apply the Cuntz semigroup, that's the same thing as the inductive limit of the Cuntz of AI. And like I said, in the classification program, most of the time, the algebras we have are inductive limits. So having this property is very, very useful. Now, in contrast, the classical Cuntz semigroup is not continuous. In fact, you can see this already with algebra of compact operators. So if you take AI to be finite dimensionals, whose inductive unit is the compact operators, you'll see very soon that this doesn't. Now, this is the case. The classical Cuntz semigroup is not continuous relative to inductive limits. And of course, for classification program, this was a major observation, the fact that now this new version has this property. In the same paper, we showed that, so if you start with your sister algebra A and you construct the Cuntz semigroup, then this has a suprema, meaning every increasing sequence in the Cuntz semigroup has a supremum which belongs to the Cuntz semigroup. And in the same paper, we show that, in fact, what we construct is a functor from the category of sister algebra to the category, we call it Q. So in fact, since then, this category has been explained in terms of axioms. In other words, we now know what properties a semigroup should satisfy in order to belong to this category. And I'm going to say more about this category during my talk today.
So could you remind...
Now, there's a question. Mm-hmm.
So could you remind me the definition of the supremum in the sense of the semigroups?
So if you have a sequence of elements, now we have an order on the Cuntz semigroup, so we know what it means to have an increasing. You ask that you ask that there is a largest element such that anything, if you have something below, you can so we start with a sequence which is increasing, say xn, such that xn plus 1 dominates xn. And now you say that there is a suprema if you can find an element y, such that every time I subtract something from it, I can fit something from the sequence between the supremum and y minus epsilon. I think I'm going to come back to this. So in my next couple of slides, I'm going to say more about this idea of a supremum of an increasing sequence.
Yes.
Okay, so again, my comparison between the Cuntz semigroup and the K-theory still is important for us in order to understand the Cuntz semigroup. So if we are working with projections, so if P and Q are projections, such that they are close. By close, I mean norm of P minus Q is strictly less than 1. then we know that the P and Q are equivalent. They are Morrey-Fonoman equivalent. And this actually tells us, this is actually very useful. And in a sense, this allows us that when you construct the K0, you can actually work, you can work instead of the algebra of compact operators, you can work with M infinity, because anything in the limit can be approximately something in the finite stages. Now, obviously, one can ask, what about the positive elements? Do we have anything like that? So let's start from the assumption that I have A and B positive elements, and in norm, they are less than epsilon. Now, the first observation is that we can say nothing about the Cuntz equivalence of these positive elements. So this is why I titled here, unlike K-theory, the Cuntz semigroup is not discrete. Now, this looks a bit surprising, so I want to explain why this is the case. And the way to do that, I'm going to look at an example. So I'm going to work with a commutative case. Usually in commutative cases, most of the time relevant. So I have my positive elements are just continuous functions on some compact space. So X is a compact space. And being positive means that the range is inside of 0 infinity. And now I'm going to say that F is Cuntz less than G. This actually can be checked, is that so-called open support. So if I look at f of x, where f of x is strictly positive, this is a subset of g of x, well, of x where g of x is strictly positive. So one can check that the Cuntz relation, the Cuntz subequivalence at the level of the continuous functions is actually amounts to showing that the open support of f is a subset of the open support of g. Now, with this in mind, I can now actually show. Question?
No.
Yes, so you call it open support, but you assume that the function. Okay, sorry. I just realized this is a stupid question. Greater than 0 is the same as different from 0, right?
Yes, yes.
Okay, sorry.
No. Yeah, because I'm assuming positive, yes. And now here's an example which shows that indeed we cannot hope for an equivalence relation like we have for projections. So I'm going to start with the following set X, for which g of x is positive, but on a small set. So what do I mean by small here? I want the proper subset and not dense, so something small. Then I'm going to build my F to be g plus epsilon over 2. So first of all, I want you to notice that indeed, if I take F of this form and g, F minus g is going to be less than epsilon. In fact, it's going to be less than epsilon over 2. I'm working with a supremum norm. So the norm is going to be the supremum norm. So obviously, F minus g is going to be less than epsilon. However, if you think about epsilon over 2 tells me that F is now strictly positive on the entire domain, because I'm adding to something g, which is positive, I'm adding epsilon over 2. So what it says that the Cuntz class of F is really the class of the constant function 1. On the other hand, if we look at G, this F is never going to be equivalent with G, simply because my G, by the assumption, was strictly positive on some small set. Right? So we can never get this type of inclusion between the constant function and G. So long story short, I'm showing here that we don't expect, if A and B are close, and epsilon can be any arbitrarily small number, we cannot expect that these are going to be equivalent in the sense of Cuntz. Now, at this stage, you may say, okay, this is the case, that looks like not being able to say much. That looks like is a big difficult situation. Now, it turns out something can be said, and this is actually, if you look at the.
Hello, Christian.
Yes.
Could you go back to the previous slide, please? Could you explain to me why this Cuntz class of F is the same as that of 1?
Yes. So what happens is, okay, so 1 is going to be strictly positive on the entire X.
Yes, of course.
Because it's a constant function. Now, my F is also strictly positive on the entire F. So the support of F is going to be...
Yes, of course. Yes, because it's it's global. Okay. So, yeah. Thank you so much. Thanks.
So, like I said, we would like to have something, and it turns out that what I'm about to say is actually present in most of the papers on the Cuntz semigroup. So it's a very useful property, which is related to when when two elements are close, two positive elements are close. So if F and G are close, then okay, we can say the following. So instead of greater than 0, I can say the set X where f of X is greater than epsilon. This is a subset of X is in X for which G of X is strictly positive. So if you pay attention, indeed, if F is greater than epsilon, because I'm working with a supremum norm, G cannot be negative. So whenever X is such that f of X is greater than epsilon, then because I'm using the supremum norm, F minus G G cannot be negative, right? Or 0, because then I'm getting equality here. So this is an inclusion which is useful because now I can say, okay, I can subtract epsilon, and then I can say that F minus epsilon, now since I want positive elements, I'm going to say maximum between F minus epsilon and 0. And then this element is going to be Cuntz less than G. So in other words, a perturbation of F is going to be less than G. I cannot get my original F, but something close, a perturbation of F, has this property. And using functional calculus, so you take f of epsilon of t to be this function, maximum of t minus epsilon and 0, you build this positive element, you apply the functional calculus and you get a minus epsilon plus. And now, thanks to a work of Rordan and Kirchbeck, so what we noticed in the commutative case was actually proved in general in the non-commutative, now than any C-star algebra. They show that if A and B positive elements are close, by that I mean their difference is less than epsilon, then a perturbation of A is going to be, yes, thank you for fixing the spelling, A minus epsilon, so this is a perturbation, is Cuntz less than B. So this is actually a statement which is present in most of the papers. So if you pick randomly a paper on Cuntz semigroup, you'll notice that they have this assumption or something very much similar to this. So it's a very useful technique. It's a very useful technical tool that people use whenever they work with Cuntz semigroup. And like I said, you can actually understand this by looking at the commutative case, where it makes easily sense. The result itself is not very easy to prove. However, it's very much used. Now, on the Cuntz semigroup, we have what is called an auxiliary operation, or sometimes called way below. And this may explain a little bit what I mean by existence of suprema. So we define that A is a Cuntz below B if whenever we have an increasing sequence Bn, increasing obviously means that Bn is less than Bn plus 1. In the Cuntz semigroup with supremum X, such that B is less than X, then there exists N such that A is less than Bn. So if you see this for the first time, then obviously this doesn't tell you much. And I will try to explain a little bit what it means, what's behind this. As you probably expect, I'm going to use the commutative case. So first of all, this compact containment, which is an operation that appears on the Cuntz semigroup but is not in the algebra, can be viewed as a separation property. And to understand why I'm saying this, again, I'm going to look at the commutative case. So I'm going to start with A and B in the continuous function over some compact space, X. Then this condition of A being compactly contained in B is equivalent with saying that the closure of the support of A is inside of the support of B. So this closure, in other words, there is room between the support of A and support of B. Initially, the Cuntz sub-equivalence requires that the open support of A is inside of the open support of B. But now we want to have some room. In other words, we want to apply, if you think about the Urison lemma, we want to be able to separate this sets. So this is the first observation. Now, maybe what is still a question is why call it compact? Why don't just say a special containment? To see that, first of all, we say that an element is compact if and only if A is compactly containing itself. And if you take that into account, then it's not very hard to see that, say in the commutative case again, saying that to have an element is compact is the same thing as saying that its open support is compact. Now, the open support that of this element is going to be compact. Very interesting here is that projections are compact elements.
Wait. So it's both open and compact?
The closure of this is compact.
That's what you mean.
Yeah. And the significance of this result is, again, a result of Ara, Pereira, and Thoms, where they show that for a nice class of sister algebras, and I'm going to mention the properties of unital, simple. So in fact, unital is important because without unital, one has to work harder. Simple, separable, stabilified, z-stable. Again, I will explain about z-stable later in my presentation what it means. Then the Cuntz semigroup has a representation. Think about GNS for a sister algebra. So it's a very similar type of idea. So the Cuntz semigroup has a representation as these are the compact elements or the projections, and these are the pure positive elements, which are represented by the semigroup of lower semi-continuous affine function on the tracial cone of the algebra. Okay, so like I said, the V sub A is going to be the compact elements, which I just explained what they are. And notice here, so I think this is an interesting observation. So for these nice sister algebras, if you know the Cuntz semigroup, that means you have this nice representation. And now you can recover the K0 group. So what you do, you take the compact elements, and that will be precisely your V sub A. And then you do the Grothendieck enveloping group to get your K0. Now, at this moment, likely some of you may say, well, what about K1? So K1, normally from the algebra itself, you cannot recover. However, if you use a trick, which is, you know that K0 of A tensor C of T, this is continuous function of the circle, is K0 plus K1, then you can actually recover K1 by using the Cuntz semigroup of A tensor C of T. Well, basically, you do the compact elements of A tensor C of T, and then apply the Grothendieck group of that. So what I'm saying is that you can actually recover modulo that you also include the continuous function of the circle. Now, I did mention the Z-stable sister algebra. So Z is a Jiangsu algebra. If you see for the first time, let me just say it's a nice sister algebra. It's an infinite dimensional version of C. By that, I mean it has the same Elliott invariant as C. So that means K0 is Z, K1 is trivial, and the tracial cone, the tracial spaces have a unique trace. So both Z and C have a unique trace. Also, Z is projectionless. I mean, it has only the 1 and 0, but it's projectionless. And the property that we have is that we say that the sister algebra is Z-stable if A tensor Z, this nice algebra which one can show it exists, is isomorphic with A. And in fact, Zhang and Su, they originally introduced this algebra. They showed in that paper that if you have such an isomorphism, then you can actually show that this isomorphism is approximately unitarily equivalent to the map, special map, A goes into A tensor 1. 1 is the unit of Z. Now, the reason I'm mentioning this technicality is because this implies nice regularity property for sister algebra, which is fundamental in the classification theory. And what do I mean by that is that, we probably want to talk about the classification. So whenever we talk about the Z or Z Jiangsu algebra, one should also talk about the classification. So the classification program was started by Mora and von Neumann. Then we had Kohn and Hagerup who did the classification of hyperfinite factors. Now on the sister algebra side, we had Gleam. And then shortly after, we have Bratteli and Elliott who classify AF algebras with, Bratteli using Bratteli diagram, Elliott using K-theory for the first time. And then maybe the list is not complete, of course, because there are many names I should have included, but it's fair to say that the names I'm posting are the ones who had major contributions. So we have Kirchberg and Phillips, who classified the purely infinite. And then we have Tiquis, White, and Winter, who had the contribution about the traces. And then maybe the heavy lifting was done by Elliott, Gong, and Lin, and New, where they completed the classification. So what it says that using K-theory and tracial spaces and the pairing, a large class of sister algebra, namely the ones I'm mentioning here, so a simple separable nuclear Z-stable, so this is the regularity property that was observed, and satisfy the UCT, they can be classified using K-theory and traces. This is what we usually call Elliott invariant. Now, at this stage, I want to point out that there are algebras which are not covered by the classification. So in particular, there are what is called Villotson algebras, which are not classified by the Elliott invariant. In other words, Elliott invariant cannot distinguish them. And in fact, what I mentioned at the very beginning, Andrew Toms, in his breakthrough paper, he actually used a Villotson algebra to show that indeed you need the Cuntz semigroup to be able to classify it. Now, at this stage, an obvious question is what additional invariant will be necessary to classify Villotson algebras? Now, of course, I didn't tell you what they are, and I'm planning to tell you about. But at the moment, let's just accept there are some algebras called Villotson algebras, which cannot be classified. Now, the additional invariant, likely you may think, well, it should be Cuntz semigroup. And I should probably state that at the moment, there is no counterexample to the statement that if you use the Elliott invariant together with the Cuntz semigroup, you have a classification. In other words, you don't have an example of algebras which say have the same Cuntz semigroup and the same Elliott invariant, and still they are not isomorphic. Now, as I mentioned already, the Cuntz semigroup tends to be a big object, very hard to handle. So thanks to Andrew Tom's work again, we have actually an information that is captured by the Cuntz semigroup and is called radius of comparison. And it turns out that this is already enough to classify certain Villotson algebras. So what I'm about to do is I'm about to tell you about a number, which is called radius of comparison, which if you add to the Elliott invariant, you can actually classify Villotson algebras, at least some of them. Okay, so what is this radius of comparison? So it's going to be a number. So this R that I want to talk about here. So we do the following. First, for stably finite, so we actually restrict ourselves to stably finite. We define the following, actually defined by Toms back in 2006. We say that A has R comparison, where this R is a positive number, if whenever we have A and B inside of the stabilization positive elements, such that d tau of A plus R is less than d tau of V for any tau, then A is less than B in the Cuntz sense. Now, of course, I should tell you what is d tau of A. So d tau of A is defined here. Now, what it is really just the rank. So let's try to do the following calculations. Think about A as being a diagonal matrix. That means you have the eigenvalues down the diagonal. Now, if you raise them to the power 1 over n and take the limit, what happens is if an eigenvalue is non-zero, that will converge to 1. So now the trace is going to pick up just the rank of A. So what you see here in a special case where A is just a positive definite matrix, this is going to be just the rank. Now, what happens is in the more complicated settings, and by that I mean algebras A are more complicated, you have various ways to define the rank. And this is d tau of B is going to actually be an example of a rank. So in a sense, the more complicated the algebra, then you have more versions of the rank of a matrix. And now what you want is you want to compare them, and you want to know if a rank of A is less than rank of B doesn't imply that A is less than B. It turns out that you can do that if you can add some gap. In other words, you want this inequality to have some freedom, in order to have R to be positive. So if there is such an R, we call this R comparison. In other words, A has R comparison. And now the radius of comparison is the infimum over all such R, where A has R comparison, if it exists. If it doesn't exist, then we call it infinity. And very interesting is that the classifiable sister algebra, in other words, the one I mentioned that they've been classified, they all have the radius of comparison 0. And in contrast, Villotson algebras, they can have non-zero radius of comparison. So now we have this number which we can try to use to see if we can read something about the classification of sister algebras. And indeed, this is the case. But first, let me try to explain what Wielandson algebras are. So these Wielandson algebras, roughly speaking, they are AH algebras, meaning they are inductive limits of homogeneous algebras. So these AI here are homogeneous algebras. Now, more precisely, homogeneous algebras are cut down. So we look at C of X tensor the algebra of compact operators, and we cut down by projections. If the projections are trivial, then we get what we call the first construction of Wielandson. If the projections are non-trivial, then we are going to get the second type. Now, I should say that I'll restrict myself to the first type, so I'm going to assume that the PI of these projections are trivial, in which case this becomes just Mn. In other words, this compact operator, when you cut down, it's going to give you just matrices over continuous functions. So like I already said, I'm going to assume that PIs are trivial projections so that we get the first class. The second class will be where you have non-trivial projections. Now, as any inductive limit, the maps play an important role. So just to give you an easy idea, so if you have complicated building blocks, like I just explained, but the maps are trivial, then the inductive limit is going to be trivial. So the maps play a very important role. And this is why next I want to tell you something about the maps. So with X compact Hausdorff space, the maps are going to be diagonals. So I'm going to assume that going from one stage to another, I have a diagonal map. Now, down the diagonal, I'm going to have, well, so this is the map, so it goes from Mn of C of X into Mk of C of couple of copies of X. As you can see, I assume the first types of projections, the cut down, are assumed to be trivial, so that's why I have Mn of X. And now, down the diagonal, I'm going to have two kinds of eigenfunctions. One of them is going to be evaluations. So I'm going to use evaluations. And this is important because eventually I want to get an inductive limit which is simple. I'll say more about this. And then there is a second kind, which is roughly speaking, is an identity map. What this does is propagate. So let's say at the final stages, I get, for instance, the stable rank is 4. I want to make sure that this propagates, or I get that the K0 has a perforation. I want to make sure that this perforation lives in an inductive limit. So this second map has a role to make sure that this perforation in K-theory goes from one stage to another. On the other hand, the evaluations are meant here to help me to get inductive limit to be simple, a simple sister algebra. Okay, so what we learned from here is that each Wielandson algebras comes with a sequence of evaluation points. And if a sequence is dense in the base space, then thanks to a result of Dadala, Nag, Nemeti, and Pashniku, we know that the inductive limit is a simple sister algebra. And that is something that we want when we construct these algebras. And now a very, well, relatively recent result of Elliott, Lee, and New, they show the following. So if we have two such Wielandson algebras, that means a priori you can have two different dense sequences using in the evaluation. Then you can actually say that the corresponding inductive limit algebra are isomorphic. So this is a classification result. If they have a same Thom's radius of comparison and isomorphic K groups. So basically what they are saying is that this number that Thom's introduced is actually sufficient, once you add it to the K0, is sufficient to classify, to distinguish these two Wielandson algebras. Now, I should point out that about the same time, I was working with Dan Kucherowski, and we obtained something similar. What is different is that, so for Elliott, Lee, and New, their space X is any compact metric space. They call it solid, meaning that a certain property of the space is also imposed. in our work with in my work with Kucherovsky, we use the Hilbert cube. So X is the Hilbert cube, and so from this point of view, ours is a special case because the Hilbert cube will be a special case of what they consider. However, in our case, we allow that the sequence have same cardinality, which means our inductive units may not be simple. So from that point of view, we have a slightly more general setting. In their setting, they have to have dense sequences. But other than that, everything is very similar. So the Hilbert cube, what we use about it is that it's a homogeneous space. It's a strong homogeneous space. So you can move from any point. So let's say you have two sets of points. You can find a homeomorphism, which takes you from one set of points to another. And in a certain sense, this is what Elliott, Lee, and New do as well. So they have what we call the marriage lemma. So they can pair these points, and they can build a unitary. Okay, so we have a similar conclusion in the end. Sorry, I cannot hear.
Do they have prenuptial agreement for the marriage lemma?
Yes. Yeah. Well, actually, in the classification program, marriage lemma is a very, very used technique. So then the corresponding inductive units are isomorphic. So we have a similar conclusion. Definitely, the result of Elliott, Lee, and New is much, much nicer and reaches more algebras. Now, what we notice is that in the classification theory, it turns out that knowing how tensor product of algebras act relative to the invariance is very important. So for this reason, one can ask the question, is it true, for instance, that the Cuntz of A tensor B is the same as a Cuntz of A tensor Cuntz of B? Now, before we try to answer this question, we probably need to ask what do we mean by the tensor product of the Cuntz semigroup. So after all, we just introduced the Cuntz semigroup as an object in a certain category. We need to pay attention and say, what is that we mean by this tensor product? Thankfully, Antoine, Pereira, and Thiel, they show that in this Cuntz category, we can define the tensor product of the Cuntz semigroups, and they show that the tensor product still belongs to the Cuntz category. So this was obviously very useful to know when you try to answer such questions. And they also show that if you have one of them of the algebras, say A is a separable AF algebras, and B is an arbitrary sister algebra, then they show that the Cuntz of A tensor B is the same as Cuntz of A tensor Cuntz of B. So this is actually very nice to know that this type of property holds at the level of the tensor product. Now, in a joint work with Elliott and Kucherovsky, we showed a similar result. So what is that we showed? We showed that if A and B and A tensor B are assumed to be simple, exact, z-stable, and very important here, stably projectionless, then we conclude that the Cuntz of A tensor B is isomorphic Cuntz of A tensor Cuntz of B. So it's important that we assume stable projectionless.
Sorry,
so not just
a natural isomorphism like in Kinef formula?
I'm actually about to say how it is actually obtained. So to a certain degree, yes, is a natural isomorphism, yes. So first of all, before I tell you about the result itself, how it's being obtained, let me say that in general, this is not the case. So the Cuntz of A tensor B is not isomorphic Cuntz of A tensor Cuntz of B. So for us, it was very important to assume the stable projectionless property. Now, I'm going to explain shortly that indeed there are situations where this is not isomorphic. And that's how I'm going to talk about the map. So crucial for us is a result due to Elliott, Santiago, and Robert, where they extend the previous representation of the Cuntz semigroup. So remember, I mentioned that the Cuntz semigroup, like the GNS, if you want for a sister algebra, you can represent it as V sub A, these are the compact elements or the projections, disjoint union with a lower semi-continuous affine function on the threshold cone. These are the pure positive elements. Now, what they did, basically, they will go beyond, so they don't assume unital as well, right? So the unital is no longer assumed. And now here is something that in a certain sense is well known. So if you have two positive elements, the spectrum of the tensor product is the product of spectrum of A times spectrum of B. And just because of this property, you can actually notice that the projection, tensor projection has to be projection. Now, projection tensor pure non-compact is going to be a pure non-compact. This is just following from this property of the spectrum. Pure non-compact tensor projection is a pure non-compact, and pure non-compact tensor pure non-compact is pure non-compact. So what I'm saying here is that when you now try to look at the map going from Cuntz of A tensor Cuntz of B into the Cuntz of A tensor B, this natural map is not injective. And the reason is because if I have a projection here and a non-projection here, that'll go in a non-projection. So there is a lot of overlapping when I take, say, non-projection with projections and vice versa. This natural map in general is surjective. So the question here is, when is it that is injective? Okay, so here are some ideas of the proof. So because we assume stable projectionless, remember that representation of the Cuntz semigroup, when I have no V of A, I have no projections. So the Cuntz semigroup is really just the semigroup of lower semi-continuous affine function on the tracial con T of A. And now it's just a question of showing that this tensor product of this semigroup of lower semi-continuous functions has the property we want. So like I said, this is the Cuntz semigroup of purely non-compact elements. Is the extended real value. So this lower semi-continuous function can take a plus infinity value, strictly positive except at 0. So at 0, they have to be 0. Okay, so key ingredients in proving this result. So this is a theorem due to Lazar and Lindenstrauss, which show that, I should say that we do first the case of metrizable Choquet, and then we drop the assumption of metrizable and show in general. If you assume the simplex, the tracial simplex is a metrizable simplex, a Choquet simplex, then Lazar and Lindenstrauss, they show that this K is the inverse limit of finite dimensional simplices. So this is a very useful observation for us. And then based on this, we can show that if I start with K1 and K2, both metrizable Choquet simplices, then the following is true. So K1 tensor K2 is going to be, first of all, I replace using Lazar and Lindenstrauss, I replace K1 and K2. And now you can actually show that this is the inverse limit of K1I tensor K2I. And then we can now state our result. Well, if you pay attention, this is really saying that Cuntz of A1 tensor Cuntz of A2 is Cuntz of A1, A2. This is just because I assume stable projectionless. So remember, V of A is 0. So normally it should be Cuntz here, but with V of A, but that is going to be 0. So that's why this is a restatement of the theorem. And now I'm going to briefly show here how it's obtained. So you basically start again from K1 is an inverse limit of K1I. So it's our finite dimensional. The same thing for K2.
Can you hear?
Sorry, I cannot hear.
But we tested it before the talk and you could hear me. So now it's shocking that now you cannot hear me. Anyway, I just have a question about this tensor product notation. What do you mean by the tensor product of this CU?
Tensor product of?
Well, you have this CU notation.
Oh, so this is the tensor product in the Cuntz category. So remember I said that the three authors, they define. So Antoine, Pereira, and Thiel, they define in the Cuntz category, they define the tensor product of Cuntz semigroup. So there is a universal property. Essentially, that's how they do it. So they show that using the universal property, they show that actually it exists in the Cuntz category.
It's monoidal structures.
Yes.
Thank you.
Okay, so obviously there are more details, but the rough idea is, or the summary is that use that this K1 and K2 are inverse limits of finite dimensional simplices. At the level of the finite dimensional simplices, you actually show that you can interchange with the inverse limit, and now you use also Cadison duality to lift this to the level of the affine functions, lower semi-continuous affine functions, which eventually proves the result we wanted. Now, in the last part of my talk, I want to talk about another application of the Cuntz semigroup. And this is related to some work that Skandalis and Cuntz originally did for relative to the K-amenable or K-nuclearity. So originally, Cuntz, back in 1983, he defined, and he said that the group G is a K-amenable if the quotient map going from the full group sister algebra to the reduced group sister algebra is a KK equivalence. Now, obviously, any amenable group is going to be K-amenable, but the converse is not true. We know that, for instance, you can check it using the free group onto generators. Similarly, Skandalis, he defined what is called K-nuclear, and he defined it as if a quotient map going from the maximal tensor product to the minimal tensor product, this map induces an isomorphism between the corresponding K groups for all sister algebra B. So you say that A is K-nuclear if this is true for any sister algebra B. Again, it's obvious if A is nuclear, then A is K-amenable, but the converse, again, is not true. So the example would be, you look at the full group sister algebra on F2. So inspired by these definitions, we introduced the following similar concept. So we say that A is Q-nuclear or Cuntz nuclear if the canonical quotient map going from the maximal tensor product to the minimal tensor product induces an isomorphism between the Cuntz semigroup of A tensor B, maximal tensor product, and the minimal tensor product for all sister algebra B. And at this stage, we had the obvious question, which is, well, can we find an example of sister algebra which is Q-nuclear but is not nuclear? And actually, we were very surprised to see that actually that's not the case. So the Cuntz semigroup apparently contains so much information that, as you're about to see, I'm going to argue that A Q-nuclear implies A is nuclear. So the nuclearity can be encoded using the Cuntz semigroup. That's kind of the point I'm trying to make here. Okay, so actually, we can also make a slightly weaker version of the Q-nuclear. So we say, by definition, A is weakly Q-nuclear if the Cuntz semigroup of the maximal tensor product is isomorphic with the minimal Cuntz semigroup of the minimal tensor product. Okay, so I think I'm
it's fine now.
Keep going. Okay, so at the moment we still don't know if these two classes, namely the ones which are Q-nuclear and weakly Q-nuclear, if we have a strict subset. In other words, we don't know if one implies, well, we know that one implies the other, but we don't know if this goes both ways. Okay. What we were able to show is the following results. So this is a joint work with Dan Kucherowski. So we show that if A and B are simple sister algebras, and if I assume A is weakly Q-nuclear, so it has the property that I mentioned earlier, which is if I look at the max and mean tensor product of A and B, the Cuntz semigroup of those are isomorphic, but not necessarily from, not the isomorphism is not necessarily induced by the quotient map. Then we show that the minimal tensor product and the maximal tensor product, they are isomorphic. And I agree, this looks a little bit surprising, and I'll try to explain how we got this result. So now an important fact that is being used here is the fact that there is a one-to-one correspondence between ideals in A and ordered ideals in Cuntz semigroup of A. So this is actually what is very important when we approach this result. And to see this, let me just say that if you have an ideal I in A, then you can get an ordered ideal. So what is an ordered ideal in the Cuntz semigroup is going to be a semigroup plus it has a hereditary property. So if you have something dominated by an element in the semigroup, then that element has to belong to the semigroup as well. So we obtain the following C of I. This is going to be an ordered ideal inside of the Cuntz semigroup. So what it is going to be just all the positive elements, classes of positive elements, subject that X is in I. Vice versa, so if I have an ordered ideal in the Cuntz semigroup, then I define my ideal to be those X's in A for which the Cuntz class of XX star is going to be in C of J. And there are, before I show you how the theorem this result is proved, there are several interesting observations corollary to the theorem. So the first one is that if you have finitely many ideals, in particular simple, then if you assume weakly nuclear, then it is exact and has the LLP, so-called local lifting property. And I'm going to say more about this in my next slides. Another observation that an application is that if I have a sister algebra which has finitely many ideals or simple, then weakly nuclear implies nuclearity of the sister algebra. So this is something that obviously looks very surprising. And finally, I'm going to argue that if I have a sister algebra which is Q-nuclear, then in fact is going to be nuclear. So now we actually can claim that this concept of Q-nuclear does encode the nuclearity of sister algebra. Okay, so how do we go about it? So remember, the key idea is that there is a one-to-one correspondence between ideals in the sister algebra and the order ideal.
I do wrong class here, the best. Działa. Nie wiem, co zamarzło, ale internet działa.
Okay, so I assume now we are back. Okay.
Okay, thank you.
Yeah. So, okay, so I think I was trying to say about how to go about proving that if you have weakly or Q-nuclear, then we get nuclearity
I don't know, because
of the sister algebra. And I think I mentioned that if you have an ideal in the sister
but it's on Jabra.
ideal in the Cuntz semigroup and vice versa. So there is a one-to-one correspondence between ideals.
Microphone is on Jabra. Ah, yes.
Piotr, I think that you are unmuted.
Yes. Okay, guys, we have serious internet problem at CISA. It collapsed twice on this.
Okay,
and just continue. Ignore our troubles.
Okay, so when for what I'm saying next is important to remember there is this one-to-one correspondence between ideals in the sister algebra and order ideals in the Cuntz semigroup. Okay, and now another important idea is that any ideal in the minimal tensor product by this quotient map pulls to an ideal in the maximal tensor product. And somehow what we are about to do here is about to count the ideals. When we assume that the Cuntz semigroup here is isomorphic with the Cuntz semigroup of the minimal tensor product, basically what we also say is that the same number of ideals will be, we have the same number of ideals in both sides. But this particular ideal cannot correspond, or this is going to be an extra ideal. So it'll be the extra ideal. And this is why most of the results I'm mentioning apply to simple or algebras with far too many ideals. Because it's basically we are doing a counting and we see that this is an extra ideal in the maximal tensor product. Okay, so like I already said, so first of all, a couple of facts which are useful. So if A and B are a simple sister algebra, then the minimal tensor product is also simple. Building on that, if A and B have far too many ideals, then the minimal tensor product has far too many ideals. And now that means the Cuntz semigroup of the minimal tensor product will have far too many ideals because of the one-to-one correspondence between the algebra and the Cuntz semigroup ideals. And now the weak Q-nuclearity implies that the Cuntz semigroups of isomorphism between the Cuntz semigroups will tell me that the Cuntz semigroup of A tensor B, the maximal tensor product, has far too many ideals. And what I was trying to tell you is that this kernel of H is going to be a non-trivial ideal which will break the counting. What's important here is that you have far too many. And then that will basically tell you that if this is non-trivial, then these two Cuntz semigroups cannot be isomorphic. Okay, so that's essentially the idea. Now, what we eventually get is that we have an isomorphism for all simple sister algebra B, or if A and B have far too many ideals. Now, at this stage, this doesn't quite imply that the sister algebra A is nuclear. In other words, I think it's still an open question that if a test algebra B is assumed just to be simple, I don't think we know that this is sufficient to deduce the nuclearity. But thankfully, we have some results of Kirchberg, which allows us to actually deduce the nuclearity as well as the LLP property and exactness. So next, I'm going to say how using some of the results of Kirchberg, we can actually get what I just mentioned as applications in earlier slides. So this is the definition of a local lifting property. Thankfully, Kirchberg gave us another equivalent way. So I'll just say it. So local lifting property means that whenever you have B and J is some ideal, we say that this is locally if for any finite dimensional subspace in A, there is a lift. By that, I mean a UCP map, which makes the diagram commutative. But thankfully, I don't need this technical way of defining, and I can just say that A has a LLP property if the maximal tensor product with B of H is isomorphic of the minimal tensor product with B of H. And in fact, this is what obviously I'm about to use. So the test algebra is B of H here. So we use B of H as a test algebra. Obviously, B of H has far too many ideals. Well, it has one ideal. And we can actually use our statement where we say if it's weakly Q-nuclear, then we get that these two are isomorphic. And then we obtain the LLP property. Now, we're again going to use the result of Kirchberg to show that if we assume far too many ideals plus weakly Q, it's weakly Cuntz, then we have exactness of the sister algebra. So here now I'm going to use as a test algebra the Kalkin algebra. So B of H quotient by K of H. K is the algebra of compact operators on some Hilbert space. And now this again, if I assume that A is weakly Q, that means I have this isomorphism of minimal and maximal tensor product with B of H quotient by K of H of the Kalkin algebra. And now we know that the maximum tensor product is always exact. So that means I do have this property, and the key is to obtain the same isomorphism we see here with the minimal tensor product, because now, again, thanks to Kirchberg, we know that that is equivalent to A being an exact sister algebra. And indeed, we can show that. Obviously, K, the algebra of compact operators is nuclear. So then when I say a maximal tensor product here, that's the same thing as the minimal tensor product. And then together with what I said earlier, we can deduce that indeed with respect to the minimal tensor product, we have this isomorphism, which means A is an exact sister algebra. Again, thanks to Kirchberg, we know that this implies exactness of the sister algebra A. And now finally, how about the nuclearity? So again, this is a very nice result back in 1993 due to Kirchberg, where he says that an algebra A is an exact sister algebra A is nuclear. So we say A is nuclear if when you take the tensor product with the opposite algebra, minim and max, these are isomorphic. Now, if A has finitely many ideals, or in particular is a simple sister algebra, then the opposite has also finitely many ideals. So that means now I can apply. So if I have weak nuclearity, I can apply the result earlier, and then I get that this is true. And then again, thanks to a Kirchberg result, I can deduce that A is a nuclear sister algebra. Now, there is a slightly different approach to this, with the same conclusion. So if I assume Q nuclear, or we find many ideals, implies nuclearity. So I'm, again, looking at the max and min tensor products. I have this quotient map. And essentially, I want to show that the kernel is trivial. That's basically saying that if it's true for any algebra B, then I get the nuclearity of A. And now, thankfully, we have a property proved by Ciupercă, Roberts, and Santiago, which shows that the Cuntz semigroup respects short exact sequences. So then we have this exact sequence at the level of the Cuntz semigroup. But now, because these two are isomorphic, then the Cuntz of kernel has to be trivial. And now, remember at the beginning, if you have something non-trivial in the algebra, then the Cuntz semigroup is going to be non-trivial. So essentially, this tells me that the kernel has to be trivial. And then I get that indeed this map has to be injective as well. And that's another way to obtain that Q nuclear implies the nuclearity of a sister algebra. Okay, and I think I know that I said I should be, how much time?
You have 10 minutes. 10 minutes.
Yeah, actually, I'm going to be probably short 10 minutes, so hopefully you have more questions for me. So I will stop here. This is what I wanted to say about. Yeah.
Okay, thank you very much. Yeah, apologies for our technical problems, but twice Jerome collapsed on us and we were cut off. So yes, we have plenty of time for questions, and since I noticed Joachim was in the audience, I hope he still is around. Joachim, do you have any questions? It's about your semigroup. Hello? Okay, no questions from Joachim. So in this case, maybe I'll first ask the room here in CISA. Ludwig, any questions from you? No. So CISA is happy. Tomek, you are showing yourself, which means you want to ask a question. Yes, please unmute yourself.
I have a very short question about this kernel on the level of Cuntz semigroups. What do you mean by the kernel in the category of Cuntz semigroups?
You mean this object here?
Yeah.
Well, it's going to be an ordered ideal inside of the Cuntz semigroup.
Mm-hmm. I see. Okay. Okay. Thank you.
That's all from you, Tomek.
I'm good.
Adam?
I have a quick question about this previous slide, about this result of Kirchberg. So this is if or if and only if?
Well, if it's nuclear, then obviously the mean and max tensor product will give you, so it's if and only if, yes. Actually,
okay.
Yeah, because if it's nuclear, then this
sure.
max and mean tensor product will be, so it's if and only if, yes.
Mm-hmm.
Okay.
The important part is that if you have something like this, do you get the nuclearity?
Yeah. The
Nuclearity implies that, yes.
Mm-hmm.
Yes.
Okay, thank you.
But you have to have this exactness assumption, right? I mean, it's not.
Yes.
By the way, can you remind me, please, what it means that the sister algebra is exact?
So when you tensor with respect to the minimal tensor product with any short exact sequence, you get an exact sequence. So let's say you have 0 goes in an ideal, goes in A, goes into the quotient. Now you tensor with your algebra, let's call it A, but each tensor product is the spatial tensor product or the minimal tensor product. You get still an exact sequence.
Now that's what I thought. So, and this you say does not imply nuclearity on it.
Oh no.
Okay. Yeah, okay.
No, so the nuclear sister algebras they form a strict subclass of the exact sister algebras.
And do you know an example of some nice exact sister algebra that is not nuclear, something, you know?
I think if we look at the free group and you look at the full group sister algebra on free group of two generators, that probably. Yeah, so if you look at the F2 and the free group on two generators and you look at the full group sister algebra, that will be an example.
Okay. Francesco, do you have any further questions?
No question.
Okay, so in this case, let me grill you for a little while. Somehow it was a little bit too fast for me. I'm talking about this proof about nuclearity, because at a certain moment, as a step of your proof, you used this weak nuclearity, but this weak nuclearity was proven under the assumptions that the sister algebras are simple, whereas your claim about nuclearity is for any sister algebra. So here I'm a bit confused. Could you please unconfuse me?
So let's say we look at this one. So I have Q nuclear implies nuclearity. So now this map is always subjective.
Correct.
So the question is, can I say something about the kernel?
Mm-hmm.
Now, obviously the kernel is an ideal.
Mm-hmm.
So I have a short exact sequence. Oh, well, I have an exact sequence here.
Yeah, that's short.
Now, we know that thanks to this three-people result, we know that when I apply the Cuntz semigroup, this exact sequence still preserved.
Mm-hmm.
So that's why we have Cuntz semigroup here, as opposed to just the exact sequence from before.
Mm-hmm.
But now these two are assumed to be isomorphic.
Mm-hmm.
So that means this ideal has to be trivial. But if this is trivial, then that's only possible if the actual algebra is trivial, because I said at the beginning, if I have a non-zero element in the algebra, then the Cuntz semigroup is going to be non-trivial.
No, actually, this part of your reasoning was crystal clear to me. I meant some earlier slides where you were using this weak. I'm kind of confused about this weak CU nuclearity.
So I assume here, right? So what happens is there is a counting on the ideals. So the first observation is that if I have an ideal in the minimal tensor product, this lifts to an ideal in the maximal tensor product. That's because I have a subjective map.
Yes, of course, yes, true. Mm-hmm.
But the kernel is basically an extra ideal. It doesn't correspond to anything in the minimal tensor product. Right, because if I look at the kernel this is going to correspond. So this is going to be in the maximal tensor product, but not in the minimal tensor product.
Mm-hmm.
Because there is going to be trivial. It's going to be 0.
Yes.
So the idea is that as long as I keep finitely many ideals, this is going to be always an extra ideal.
Correct. Mm-hmm. Mm-hmm.
Now, the weakly Q or even Q nuclearity tells me that these two have the same Cuntz semigroup.
Okay.
Which means they have the same number of ideals.
Okay.
But we just argue that this is an extra ideal.
Yes. Yeah.
So this is why I'm actually insisting that I either assume simple or finitely many ideals. The moment I allow infinitely many ideals, this argument fails. Or at least you cannot use it.
Okay, but isn't your statement true for arbitrary sister algebras?
Well, when I
mean,
well, there are some assumptions. Obviously I have some assumptions. So in the first instance, I assume either simple or I assume finitely many ideals. It's only at the very end where I can actually say, as long as I assume just say a basic, which is exactness, then I can obtain nuclearity. Right. So at the very end, I'm actually having a more general setting. Well, so first exactness, and then I'm using this.
So wait, so at the end of the day, you always have some assumptions for a statement that CO nuclear implies nuclear.
Yes.
Okay.
Yes.
Okay, it's either exactness or finding many ideals or being simple. Okay, I think I have one last question. You always used, I mean, maybe not always, you often used commutative sister algebras to exemplify what happens in the world of Cuntz semigroups. How about graph sister algebras? They are also very tangible and something you can very easily. I'm sorry, I'm obsessed with graph algebras. Can you exemplify some mechanisms that happen with Cuntz semigroups on graph sister algebras? I mean, K-theory is given to you on the plate when you talk graph sister.
Well, I think if I'm not okay, so the way I know is that the graph sister algebra tend to be either purely infinite. Is that correct?
Yeah, they can be purely infinite, surely.
In that case, the Cuntz semigroup is going to be just 0 and infinity. So it's somehow close to being trivial. So if I look at the graph sister algebras, which are purely infinite, then the Cuntz semigroup is, well, if it's a purely infinite algebra, the Cuntz semigroup is going to be just the class of 0 and the class of infinity. Because being purely infinite means all the positive elements will be equivalent to the infinity.
But what if it's not infinite? I mean, I'm sure you can have plenty which are not purely infinite.
If it's AF algebra, I think that's another class I am aware of. So if it's a graph sister algebra which is AF algebra, I think that would be an interesting situation. The Cuntz semigroup is very well understood because in the real rank 0, we have a good understanding of the Cuntz semigroup. So you could probably say, you can actually use the Cuntz semigroup to understand the structure, especially if it's not simple. So in the non-simple case for graph sister algebras, which are AF algebras, I think Cuntz semigroup could be used to understand the objects.
Okay, but how about something like the sister algebra of quantum SU2 group? I mean, it's definitely not AF, and I don't believe it's purely infinite. So it's just a typical, Q geometry sister algebra. You have a circle of characters inside. You have compact operators. There's type 1 sister algebra. There's nice K theory. You can go to Podley spheres. I mean, it's a natural non-commutative topology examples, and they happen to be graph sister algebras as far as their structures.
Do you know if these algebras are Z-stable, like they are classifiable?
I don't believe they are Z-stable. I don't know, but I would be surprised.
Because that makes a big difference. So if it's Z-stable, then we can say quite a bit about the Cuntz semigroup. If it's not Z-stable, I think the Cuntz semigroup probably will be very complicated.
But the commutative examples were, of course, not Z-stable, right? So somehow I was hoping that also in this case, even though you do not have Z-stability, you do not have simplicity, but you have some very explicit structure, especially when K theory is concerned on the plate, that maybe something would be known. But
if it's not simple, I suspect that the Cuntz semigroup can be useful because the Cuntz semigroup, unlike K theory, can pick up on the ideals. So the information on the ideals can be actually, you can read it in the Cuntz semigroup.
So what I remember, but we wouldn't need the Soren or Szymanski, is that The simple ones are stable, so that the simple graph system algebra is stable. I don't know if there is some expert that can correct me. And that the simple ones and the AF ones are also the ones that are classified by case theory. So then maybe you don't need in the case the Cuntz semigroups, semigroup, I guess. But,
Right.
I don't know if there is any expert online of graph system algebras.
Okay, thank you, Francesco. Okay, if there are no further questions, I don't see any raised hands, then let us thank Christian again for his very exciting and interesting talk. Thank you so much. Let me stop recording.